Hello everyone, welcome back. We're on chapter 5, which means we are about halfway through the class. Crazy, I know. We have up to chapter 10 for this class and then we're done. It's going pretty quick. Chapter 5, no real math, so it's still a break from the math. We won't get back to math until kind of chapter 7, definitely chapter 8, and the rest of the course. So enjoy it if you're not a math person. We're going to start today's lecture with another mini history lesson, and I'll point out along the way the different vocabulary words that you're going to need to know. In chapter 4, we talked about the structure of the atom. We talked about the different models that existed that led to the current quantum mechanical model that we have today. Along with that, remember, elements are being discovered. We've got people working on how to organize the periodic table. So the periodic table that you use for your exams didn't always look like that. So we're going to open with talking about the different methods that folks suggested for organizing the periodic table. And then we're going to move on to talking about trends of the periodic table, a different way to write electron configurations, which is a lot shorter. And we're going to introduce ions. So that's pretty much all of chapter 5. Here we go. As promised, we're going to start with a history lesson. So the first proposal that we're going to talk about in terms of classifying and organizing the elements, we're going to talk about triads. So there's a German chemist who observed that elements could be grouped in groups of 3, triads. And those elements showed very similar chemical properties and an orderly trend in physical properties. So that's the first thing that you need to know. I am not going to try to pronounce this man's name because I know I'm going to destroy it. But you should know about the groups of 3 or triads, and that when you arrange the elements in a triad, they show similar chemical properties and orderly trends in physical properties. The next suggestion was saying, hey, we have 62 known elements. Let's arrange them in groups of 7 according to increasing atomic mass. This law or theory is the law of octaves. So you're going to want to know this one too. So the law of octaves, we're saying that you arrange the elements in groups of 7 according to increasing atomic mass. The 8th element would repeat the properties of the first one in the group. So if you had element A, B, C, D, E, F, and G, that's 7 elements. The next element, H, would have similar properties to A. So you see how we're starting to form these columns of elements. And he's saying that every 8th element would repeat the properties of the first group. So know the law of octaves. Then a man named Mendeleev proposed that the properties of chemical elements repeat at regular intervals when arranged according to increasing atomic mass. So someone said, hey, these properties are going to repeat simply because we're increasing in atomic mass. And he arranged his periodic table by the formula of the element's oxide. So with all these metals and things, you can add oxygen. And the formula for that is going to be similar for elements that perform similar chemistry. So we credit Mendeleev as the architect of the modern periodic table. You're going to want to know that. You're also going to want to know how he organized the periodic table. So he had groups 1 through 8. Know your Roman numerals. And these were the generic formulas of the oxides. So the R is equal to, you put in your element there. So for hydrogen, it would look like this, H2O, water. For lithium, L2O. And so all of these have the same formula when they're combined with oxygen. You notice that there are some dashes here, and there are some eka things here. These are areas where the eka areas are where Mendeleev was able to predict the existence of unknown elements. So his periodic table was able to predict, hey, you know, there should be some other elements here. We just don't know about them yet. And this is the first time that this happened because all the other ones were just really focused on what we already had. But Mendeleev's table showed what we didn't know, or at least some of what we didn't know. So he was able to predict germanium, which is what we call it now. And he was able to predict, these are his predicted properties of germanium. And you'll notice they're pretty close. So very high back in the day, obviously, heating something up to almost 1,000 degrees Celsius. Not exactly easy. And measuring that? No. But with the limited stuff that they did have, my goodness, they were able to do a lot. The periodic table was expanded by one group to the far right when argon was discovered. So the periodic table was rearranged a little bit. We added in the noble gases. So helium, neon, krypton, that's group 8A. Those are all the noble gases. They were originally called inert gases. But since then, we've been able to make compounds with some of them, so we call them noble gases. It's not easy, but some of them will do some chemistry. There's one more change that was made to the periodic table that got us to where we are today. H.G.J. Moseley discovered that the nuclear charge, aka the number of protons, increased by 1 for each element on the periodic table. And what he said was, let's arrange it by that, the nuclear charge, which we call the atomic number, instead of atomic mass, because that will clear up some of the trends on the periodic table a little bit better. So to define the periodic law, which is what you will need to know, it states that properties of elements recur in a repeating pattern when arranged according to increasing atomic number. So you'll want to know that one. And that combined with the concept of energy levels that was introduced by Niels Bohr, remember chapter 4, the Bohr model of the atom, that made the periodic table take its current shape. History is real, y'all. Now we're going to talk about the periodic table some more and some of the trends that you're able to see just based off of the arrangement of the elements. Here's some terminology for you. The groups that I was referring to, like group 8A, groups are vertical columns. And the elements in a group have similar chemical properties. You'll sometimes see groups referred to as families. I'm going to try hard to stick to groups. Periods are the horizontal rows, so going from left to right. So vertical columns, we're talking about up and down. Horizontal, left to right. There's no real rhyme or reason to the properties of elements that are in the same period. The way that I remember which is which is I write this little mnemonic. So the group is the one that's going up and down, and a period is left to right. So that helps me remember which is which. Now we're going to talk about some of the common names and things for some of the groups on the periodic table and some of the areas on the periodic table. You'll definitely want to know these, and I have another few slides that outlines these things in words, but I'm going to go through them all here, and then we'll go through them again sort of as we go through the slides with words. This is a good time to pull out a periodic table and start labeling it. You're going to need one for all the common names, and then you're going to need another one, most likely, for the trends that we're going to talk about after this. So I'm going to start with the common names and the groups. Notice that there's these Roman numerals with the letter A. I'm circling them now. All of those are what's called the representative elements. I know I'm not going to be able to fit this word. Okay. All of the B elements, let me do this in a different color so you can see it. Those are your transition elements. And if you think about where they are in terms of the different blocks we talked about with electron configurations, the A elements are the S and P block elements. The transition elements, those are the D block. Then we have the inner transition metals. That's the F block. So this is trying to help you relate the information from chapter 4 to chapter 5, because at the end of all this, you're going to have a final exam, and it's cumulative. So that exam is going to test not just, can you do problems, but can you kind of string together all the information to answer questions. Within the inner transition metals, you have the lanthanides and the actinides. So the lanthanides, that's the top row, the actinides, the bottom row. Finally, there are some group names that are common, okay? Group 1A, those are the alkali metals. They are highly reactive. Group 2A, that's the alkaline earth metals. Those are pretty reactive too. There's no common names really for any of these guys. But once you get to group 7A, those are the halogens. And group 8A, those are the noble gases. Right here. So as I promised, there's going to be all of this in words coming up. So we've got representative elements, as I said, the A groups. Transition elements are the B groups. Intertransition elements, those are the ones below the table. They're also called rare earth elements, so you might see both. And those are divided into lanthanides and actinides. These are the common names for the groups. So this notation is kind of newer. This is the IUPAC group numbers 1 through 18. You'll also see the numbers with the letters on the periodic table. I think the letter system is a little bit more helpful when it comes to understanding the different groups inside of the periodic table. But it's totally up to you. Whichever one makes the most sense, that's the one that you remember, and that's the one that you refer to. Now we're on to periodic trends. So there's a few of them, and I'll point out when you should be adding something to your periodic table. Like now, we're going to talk about atomic radius. So what you're going to want to draw on your periodic table, preferably in different colors. You're going to have one color for atomic radius. And as you go up a group, so from the bottom of a group to the top, and as you go across a period from left to right, atomic radius decreases. So atomic radius, we're talking about the size of the atom. How big is it? This is a visual representation. Now, this trend does not include the transition elements, okay? It's only for the representative elements. So keep that in mind. And as we go up, we see the decrease. And as we go across, ignoring the transition elements, the size decreases. But why? So as you go from the bottom to top, there's fewer energy levels. So remember, if we have all of these energy levels, which each row on the periodic table corresponds to, the higher the energy level, the farther away the electrons are from the nucleus. So that means it's bigger. So if we had n equals 1 versus n equals 5, with our little nucleus in the center, you can already think about, oh yeah, that makes sense. It gets bigger, right? Now, as you go from left to right across the periodic table, you're not increasing the number of energy levels, but you are increasing the number of protons in the nucleus. So as you go across the table, you're increasing your atomic number, and those protons will draw their electrons in closer. So that's why the radius gets smaller as you travel from left to right. The protons are drawing in those electrons a little bit more snugly to the nucleus. The next trend you're going to want to put on your periodic table in a different color from the atomic radius is metallic character. And this is just how easily an element is willing to give up an electron from its outermost energy level. As you go from the bottom to the top and from the left to the right, your metallic character decreases. So it's the same type of trend as atomic radius. It decreases from bottom to top and left to right. So this is an example of what your periodic table should look like. Obviously not in the pseudo 3D like it is here. We're going to take a little bit of a break from drawing on the periodic table and talk about the properties of the elements in the groups. Since the elements follow a regular pattern in terms of chemical and physical properties, we can predict unknown properties of an element based on the elements around it. So let's say that we've got all of these elements. Okay, this is group 1A. Lithium, sodium, potassium. We've got their atomic radius, their densities, melting points, atomic mass. What you can notice is that, again, the trends that we're talking about, as you go from the bottom to the top, the atomic radius is decreasing. For density, we're seeing a similar trend. Now, there is a little bit of fluctuation here with sodium and potassium, and that's common. But overall, you're going to see the same trends. So as you go from the bottom to the top, you see a decrease in the density. And this is just for group 1A. Doesn't mean that the density is always going to decrease as you go from the bottom of the group to the top. Same thing for the melting point. This trend doesn't have to hold true for every group. This is just group 1A. So as you go from the bottom of group 1A to the top of group 1A, we're seeing an increase in the melting point. And for atomic mass, we're again seeing a decrease. Cesium is not the last element in the periodic table in group 1A. Francium is. So we can predict that, okay, francium comes after cesium, so its atomic radius is going to be bigger than 266 picometers. Its density is likely going to be bigger than 1.87 grams per milliliter. Its melting point is going to be less then 28.4 degrees Celsius, because that's what the trend is, right? We're increasing from bottom to top in this particular group. And the atomic mass is going to be bigger than 132.91. So that's what we mean. Now let's say that we didn't have the information for let's say we didn't have the information for cesium, but we had all the information for francium. You could do the same thing, that cesium, its atomic radius, would be somewhere between the radius that we have for rubidium and for francium. That the density would be between the density of rubidium and francium. You see what I'm saying? So you can predict the physical properties based on the elements in that elements group. We can also do the same thing with chemical properties. And remember, Mendeleev already kind of did this because he organized his periodic table according to the formula of the oxides of the elements. Forming an oxide, that's a chemical property. So all of the alkaline metals have the same general formula of M2O, where M is equal to whatever your element is. And again, this is something that Mendeleev observed. So here's a practice question for predicting chemical properties. The formula for chloride of calcium is CaCl2. What is the formula for the chloride of barium? What you have to know, and this is by looking at the periodic table, barium is in the same group as calcium. So if they're in the same group, we can make a prediction. If they're not in the same group, then we can't. But since they are, we can predict that the formula for the chloride of barium is going to be very similar to the formula for the chloride of calcium. So these questions may seem really complicated or like, how can I answer that? It's not. As long as they're in the same group, they're going to follow a similar trend. So this periodic table shows the different blocks like we were talking about in chapter 4, and it combines the names for some of the elements. So the representative elements, transition elements, intertransition elements. This is a nice visualization, and it can help you a little bit with writing configurations. So if this looks good to you and you want to print it out in color for yourself, go for it. Stick it in your notebook. So in chapter 4, we wrote these really long electron configurations, and those are the full electron configurations where we wrote every little thing down. There's another way to do it, and that's the noble gas electron configuration, which you may see as the condensed or abbreviated, all the same thing. We're first going to practice writing the full configuration. Then we're going to take that and write the noble gas configuration. So we're going to use sodium. How many electrons does it have? If the atomic number is 11, that means we have 11 protons. And in a neutral atom, the number of protons is equal to the number of electrons. So we've got 11 electrons to place. Now this would be a good time to practice writing full configurations. So you can pause the video and write out what you think the full configuration for sodium is. I highly recommend it. But if you don't, that's okay. I won't know, but I know some of you ain't gonna do it. That's okay. Here we go. I'm not gonna label the periodic table like I did in chapter 4. So if you're still struggling with that, watch the chapter 4 lecture again, or check out that video that I posted for the electron configurations, because that covers both the full configuration and the noble gas configuration. So we're going to start at the beginning, which is the best place, right? We're going to fill the 1s. We're not at sodium yet, so we have to start filling the second main energy level. We fill the S sublevel. We go across and fill the P. Now we're at sodium, so we're going to stop at 3s1. So that is the full configuration for sodium. I'm going to abbreviate the noble gas configuration with Ng. To write the noble gas configuration, what you do is say, okay, sodium, that's in period 3. I'm going to look at the noble gas in the period before that. So period 2, the noble gas, remember these are the noble gases. The one that comes before it is neon. If you were to write out the electron configuration for neon, it would be 1s2, 2s2, 2p6. So that, just writing neon in brackets, means 1s2, 2s2, 2p6. Now we just have to add on the electrons in the row that sodium is in. 3s1. Much easier, much shorter, I know. Let's do another one. This time we're going to do sulfur. Pause for a minute. Write out the full configuration for sulfur, which I'm going to do. And then we'll write out the noble gas configuration. We have to place 16 electrons for sulfur. Starting at the beginning, we fill the 1s. Now we start filling the second main energy level, starting with the S sublevel, and we fill that. Then we fill the P sublevel, and we're still not there. We fill in the 3s sublevel. Then we arrive at 3p, and that's the home of sulfur. So we should count 1, 2, 3, 4. That's the full configuration. For the noble gas configuration, we're going to take note of which period we're in. We're still in period 3. So that means we're going to look at the noble gas in period 2. So our core is neon. Notice it's still the same. Then we just have to figure out what the third row is until we have to figure out what's between neon and sulfur. And that is 3s2, 3p4. So we did 2 examples of 2 different elements. They have the same core, but there's a difference in what's left. Those electrons that are left are the valence electrons. They're the outermost principal energy level electrons. And these are the electrons that are involved in chemistry. And again, like I said, the valence electrons are the s and p electrons that go beyond the noble gas core. This was sodium. Your valence electrons, which in this case there's only one, is going to be the electron that's in the 3s. For sulfur, we have 6 valence electrons because the 3s and the 3p are the outermost principal energy level of the atom. Now there's a way to predict valence electrons, and this is sort of a trend. If you want to put it on your periodic table, you can. I said earlier that I like the Roman numeral in the American convention, and that's because if you look at the Roman numeral, that will tell you the number of valence electrons for the representative elements. So if you're in group 1A, everything in group 1A has 1 valence electron. Everything in 2A has 2 valence electrons. If you were to go over to group 7A, it has 7 valence electrons. So it's a really easy way to know how many valence electrons you have for a particular atom. If you want to include this trend on your periodic table, as you go up the group, your valence electrons remain the same. As you go across a period, you're going to increase. But again, this is only for the representative elements, which I'm going to write the A elements just for space, and to remind you that the representative elements have an A after their group number. So the valence electron prediction, this only works for the representative elements. Don't try it with the transition elements. We can represent the valence electrons visually using what's called an electron dot formula or a Lewis dot structure. I was taught Lewis dot structure and won't know generic electron dot formula. Lewis got his credit, okay? The way that you write these is by writing the symbol of the element and then using dots around the element to represent the electrons that are in the valence shell. So if we took our example with sodium, and again, this was our configuration, the noble gas configuration for sodium. This means that we have 1 valence electron. So we're literally just going to put a dot. And that is the Lewis dot structure. For sulfur, we said that all of the valence electrons are the S and the P in the 3rd energy level. That's a total of 6 valence electrons. So we have to place 6. When you have more than 4 valence electrons, you don't want to pair up until you have to. So notice how I just went around until I filled in everything. That's the best way to do it, to make sure that you write it properly. Because if you write this, that's wrong. Electrons do not want to be paired unless they absolutely have to. So if growing up you had family coming in from out of town and you didn't have guest bedrooms, because I certainly didn't grow up like that, still don't have it. If family visits, we got to shuffle around. When I was a kid, we have family coming up from Georgia or Virginia. That means you're sharing your bed. Doesn't matter that it's a twin size mattress and that somebody's feet is going to be by your head. You're sharing. Electrons don't want to do that, just like you didn't want to share your bed with your cousin, because after that 12-hour drive, they didn't wash between their toes. You don't want that by your face while you're trying to sleep for 8 hours. The electrons don't want it either. So hopefully that will help you remember. Do not pair up electrons in your electron dot formula unless you have to. So let's do another example. Let's do phosphorus. Oh, you know I don't like to use red. Why'd you let me use red? So the element symbol for phosphorus is P. It is a group 5A element, which means it has 5 valence electrons. So we don't even have to look at the periodic table. If we're told this is a group blah A element, then we know that it has blah valence electrons. So we have to place 5 electrons around the phosphorus symbol. We fill in 1, 2, 3, 4. Still not enough. So sorry, electron, you got to share the bed, okay? Likewise, that would be acceptable too. So as long as there's only 1 electron pair and then 3 lone electrons, you're good to go. This brings us to our next periodic table trend, a real one that you definitely want to put on your periodic table. Ionization energy, which is related to valence electrons. The ionization energy of an atom is the amount of energy required to remove an electron in the gaseous state. Now we're talking about valence electrons because those are the ones that do chemistry. As you go from the bottom to the top of a group and from left to right, your ionization energy will increase. So it is different from atomic radius and metallic character. Ionization increases as you go up a group and across a period. So this is what that looks like. And remember, we can kind of make sense of this. The radius down at the bottom is going to be really, really big with our nucleus in the center. So if we have electrons hanging out here, they're not exactly closely associated with the nucleus. So it's going to be a lot easier to ionize an electron when it's far away from the nucleus. But if you have an atom with a smaller nucleus, or excuse me, a smaller radius, those electrons are much closer to the nucleus. So it's a lot harder to remove an electron here because the attraction is greater. And likewise, since the atomic radius decreases across the periodic table as well, we have the same issue. The electrons are much more closely associated with the nucleus. That means that atom doesn't want to give them up. Ionization energy leads us to talking about ionic charges, because if you remove an electron, you're no longer a neutral atom anymore. You have a charge because the number of protons and electrons is no longer equal. We're first going to talk about positive ions. Most of the periodic table contains metals. Metals react by losing their valence electrons. So if we have sodium, and this is the full configuration, and we said the outermost electrons are the valence electrons, if we lose those, now we have a positive ion. Because instead of having 11 electrons and 11 protons, we now have 10 electrons and 11 protons, which means we have a positive 1 charge. And that is represented here. So you have the element symbol, and then as a superscript, you have the charge. In general, the ionic charge of a metal representative element is equal to the group number. So sodium is in group 1A. That means all group 1A metals have a +1 charge. If you were a group 2A metal, it would be +2 charge. Notice how if we write out that noble gas configuration, it helps tremendously with identifying the valence electrons, and we can see what our core is going to look like. So neon only has 10 electrons. It has 10 protons and 10 electrons. We don't care about how many protons neon has, but we care that it has 10 electrons because that tells us how many our sodium atom, that's a positive ion, is going to have. Let's do an example. Write the charge and electron configuration for a calcium ion. Find calcium. It's in group 2A. So right away, we know the charge. You write the symbol, and then you write the charge as a superscript. So that's that part. Now we need to write the electron configuration, and I will write out the full configuration and the noble gas configuration just because the practice is really good. So take a second, pause the video, and try writing out the configuration for calcium. At this point, I don't even care if you do it for the ion. Just try it for calcium. We're going to write it for the ion. but you can write it for just plain old calcium if you want to. So here we go. Calcium, the ion, has lost 2 electrons. It's lost its valence electrons. So if we write out the full electron configuration for calcium, the neutral atom, we start with 1s2. We fill up the 2s and the 2p. We then fill up the 3s and the 3p. And then we'd fill the 4s and we'd call it done. But where are the valence electrons? The valence electrons are the outermost electrons in the outermost energy level. These are our valence electrons. That means that the ion is going to be this. Because we're going to get rid of those valence electrons. If we were to write the noble gas configuration for the neutral calcium atom, we would say, okay, I am in the 4th row, so I need to go find the noble gas in the 3rd row. That's argon. Then I add on my 4s2 to get me from argon to calcium. All right, that's the noble gas for calcium, the neutral atom. If we're going to write the noble gas configuration for the ion, we already know that these are the valence electrons. So what we do is get rid of those and simply write the noble gas core. So both of those say the same thing. On an exam or on your homework, it's going to specify which electron configuration, but I wanted to write both simply so that you have the practice. And you can see how you can transition from the full electron configuration to the noble gas, and to go from the full electron configuration for the neutral atom to the ion. Now we're going to talk about negative ions. So metals, that's most of the periodic table. But once you get to that far right, we're talking about nonmetals. So we're talking about things like carbon. Well, we're not going to include carbon in this. Carbon is a little bit different. It is a nonmetal, but carbon is a little bit different. We're definitely talking about oxygen, though. Sulfur, fluorine. Nonmetals gain electrons to form negative ions. So they're trying to look like the noble gas in their row. And you'll see what I mean in just a minute. Here we have the full notation for oxygen. We're going to add 2 electrons to complete the 2p sublevel, because that's where we can fit 2 more electrons. So the name of the game is complete the sublevel of the main energy level that you're in. Now, instead of having 8 electrons, we've got 10 electrons. So the charge is -2. The way that you can figure this out without writing out the configurations is that for a non-metal representative element, you take the group number, and we're talking about the number with the A behind it, and subtract 8. Oxygen is in group 6A. Its charge is -2. So that means if you're in group 6A, your charge is going to be -2. Let's try chlorine. Chlorine is in group 7A. So that means to figure out its charge, we're going to take the 7 and subtract 8. That gives us -1. Easy. That's chlorine. Now we're going to do the electron configurations, both the full and the noble gas. Let's start with the full configuration. And we're going to write it for the neutral atom first. Always start here at the beginning. Fill the 1s. Then you're going to fill the 2s and the 2p. Fill the 3s. Now we're in the 3p. So we're going to slow down and count. 1, 2, 3, 4, 5. 3p5. We're adding an electron here. So to add an electron, it's going to look like argon. So we're going to write out 1s2, 2s2, 2p6, 3s2. All of that is the same. But we're going to add 1 electron to complete the p sublevel. And now that means that we have 18 electrons and 17 protons. So we have a -1 charge. If we were to write the noble gas configuration for the neutral atom, we would be looking at neon and then filling in, we'd be looking at neon and filling in everything between neon and chlorine. However, for the noble gas configuration for the ion, and this is negative ions, you're going to look like the noble gas in your row because that's what you're achieving. So chlorine gained 1 electron, and now it has the same configuration as argon. We're going to do practice on this in class, I promise. Here's a handy little chart that has some of the common ionic charges. You won't have this on the exam, so don't rely on it. But it will come in handy for chapter 6 when we start doing naming and writing chemical formulas. So if you don't understand forming ions from chapter 5, chapter 6 is going to be difficult because you need that concept in order to name. The last concept for chapter 5 is what's called an isoelectronic series. So atoms and ions with the same electron configuration are what's called isoelectronic. Iso meaning same. All of these atoms and ions have 18 electrons, and they are isoelectronic with argon, which is a noble gas. And that should ring true to you because chlorine is in this list, and we just did the chlorine ion and said it looks like argon. We also did calcium and said that it looked like argon. So if you're like, wait, what? Go back and look. We already covered that. I'm sneaky. But let's write it out for 2 different ions. So we've got the phosphorus ion and the potassium ion. We'll start with phosphorus because that one, usually the negative ions are a little bit harder to wrap your mind around. So here we are with phosphorus. It's in group 5A. So just to review the charges, we're going to take 5 minus 8, and that equals -3. So that's how we get that phosphorus has a -3 charge. What this tells us is that we're going to take the configuration for neutral phosphorus and add 3 electrons. So if we write out the full configuration for phosphorus, it would be 1s2, 2s2, 2p6, 3s2, 3p3. So this is just for phosphorus. If we add 3 electrons, the only place we can do that is in the P because that's the only one that isn't full. When you add 3 electrons, it's like jumping forward 3 spaces on the periodic table in terms of the configuration. So 1, 2, 3. We look like argon. So if you were to write out the full configuration for argon, that's what it would be. Now let's go through potassium. I'll do potassium in a different color. So there's potassium. It's in the 4th row. Let's first write our full electron configuration for potassium, the neutral ion. Now, potassium is a metal, so that means it's going to lose electrons to form its ion. These are the valence electrons for potassium. When we get rid of these, this is what our new configuration is. Interesting. That also looks like argon. But in this case, we lost a valence electron. To achieve the same configuration. So you'll need to be able to construct an isoelectronic series. So if I asked you to give me two ions that are isoelectronic with neon per se, you would need to be able to tell me, okay, well that would be, a sodium ion and a fluorine ion. Don't worry, we're going to do examples. I know you're like, wait, whoa, you can't just pull that out like that. Yes, I can, but I'm not going to do that to you when we do our live lecture. So, that's the isoelectronic series. I did not include in here a reminder slide because I forgot. I know, it's kind of ironic. But the big thing that you have is you have an exam 2 that's going to be available September 23rd through the 25th, the same way that we did before. I'm anticipating that you will likely not watch this lecture until after you've taken your exam, and that's okay. But I'm putting it in there just in case. You also have Chapter 5, Mastering Chemistry homework. I'm not going to assign a chapter check-in. You have an exam. I don't want to do that to you. If you need help with Chapter 5, you should definitely reach out. But I will not do the chapter check-in. Just do the Mastering Chemistry. That's all that I've got for you, as evidenced by the end of the slideshow. So I'll see you in class.